Welcome back to this short summary of what we have been doing the last couple of weeks, which is weeks 2 and 3 of our course on Boltzmann law, physics to computing. Now, in week 2, if you remember, the first lecture we started by introducing this sampling method, this time sampling, which works in this n space, but allows us to get accurate results for the response in this 2 to the n space. As you know, one of the basic points I've always stressed is how 2 to the n can be huge when you scale up. That tells you the total number of configurations, whereas n is the number of bits. And this method, this time sampling method, is what we introduced in this first lecture. And then we discussed how you can control these response in this 2 to the n space by adjusting the x and w, which is the bias and the weight, which are in n space. So those are the things that control this response in the 2 to the n space. And then in the third lecture, we talked about how you could design x and w to solve useful problems, to give you this optimal solution in a whole class of problems that you generally refer to as constrained optimization. We took a very specific example, this max cut and min cut problem, but the general class of problems is involving optimization. And then in the last 2 lectures, we talked about how you could use x and w, again design them to give you multiple peaks in the 2 to the n space, which could be used for inference and logic. So that's kind of what this week 2 was about. And in week 3, we introduced this transition matrix method. You see, in week 2, we had these 2 methods, namely the direct Boltzmann probabilities and the sampling method. Now, in week 3, we introduced this new idea, the transition matrix, from which also you could calculate the stationary probability distribution. And we use that first to discuss this whole sampling method and why it works, why it is important to update them sequentially, and simultaneous updating doesn't work, and so on. And then in the 4th lecture, we talked about these Bayesian networks. You see, in general, we have been talking about Boltzmann networks, which are reciprocal. So if there's a W12, there's a W21. The two are equal. Whereas these Bayesian networks, which are also widely used, although we don't talk much about it, in those networks you don't really have a Boltzmann principle because you cannot write an energy function. But you can still use the same sampling methods, you can use the W matrix method, and you can compare that with what you get from the Bayes theorem. And finally, we talked about this Feynman paths, which gives you a nice conceptual picture of how to think about these probabilistic circuits using these W matrices, and it provides you a conceptual bridge to our next topic, which is about quantum computing, which is what we'll be doing in the last 2 weeks of this course. Thank you.